In this video, we're going to define three unit vectors related to a space curve: the unit tangent vector, the unit normal vector, and the unit binormal vector. So to set up our development of these three vectors, we're going to start by supposing that I have a vector function r of t, which is smooth. At some particular value t0. So quickly, let's remember what we mean by smooth. What we mean here is that r prime is continuous at t0, at t naught, and that r prime of t naught is not equal to 0. So this function is at this particular time t naught, this vector function, the derivative is continuous and non-zero. So if that's the case, then we know that r prime of t naught is tangent to the curve C that's sketched out by the function r at the point r of t naught. Right? So r of t naught describes the point on the curve. R prime of t naught is the tangent direction. And then we also know that the magnitude of r prime of t naught is not equal to 0. Okay? So we have a non-zero vector here. And so what I have is I have this vector that is tangent to the curve, and I have a non-zero magnitude. And so what we can do is if we take that vector, r prime of t naught, and we divide it by its magnitude, or we scale it by 1 over its magnitude, we get a unit vector. Right, so this is a unit vector. It's a vector of length 1. So we took a vector, a non-zero vector, we divided it, each component by its magnitude, and therefore the new magnitude would be 1. And not only is it a unit vector, it's a unit vector that's in the same direction as the vector r prime of t naught, the tangent vector. And so what we've just created is a vector which is a unit vector and a tangent vector, and therefore a unit tangent vector. Right, so we'll give this a formal definition. So we're defining the unit tangent vector. Which we're going to define with a capital T. So T of t. And we do need of a smooth curve. Given by r of t. And it's the vector that we just developed. We're going to take r prime of t divided by its magnitude. Right? And this is for any point t. So we've actually defined not just at a particular point, but we've defined it at every point at which this curve is smooth. Before we do an example of this, I want to answer a question that you might be asking yourself specifically about why are we doing this right now? We were just talking about arc length and the arc length parameter, and this doesn't seem to have anything to do with that. Although it does, although it's kind of hidden behind the scenes. And so I want to just take a second and kind of point out why this is, one of the reasons why the arc length parameter is actually a really nice parameter to use. So in this definition, I had some smooth curve r of t. T was just the given parameter. we know that there is an arc length parameter, S. But we don't actually have to compute it in order to do what we're about to do. We just need to know that it exists. And so if we let S be the arc length parameter for our function R, well, then we get the following. All right, we're going to compute R prime of S. All right, so S here is the arc length parameter. Okay. Well, I'm going to rewrite this using the other notation. So this is going to be dr ds. All right, R is a vector. So dr ds. Now, we know R is given in terms of t. So one way we can write dr ds is to first write dr in terms of dt, and then multiply that by dt ds. Right? So this is just the chain rule. This is the very standard form of the chain rule. If you write R in terms of a variable and then that variable in terms of a second variable, and you multiply those derivatives together, you do get the derivative with respect to that second variable. So I'm using the chain rule here. And now the first derivative, dr dt, this is just R prime of t. Right, so I'm just going to replace dr dt with R prime of t times dt ds. So one thing we can do at this point is we can rewrite multiplying by dt ds as dividing by ds dt. All right, so algebraically, we're just, instead of multiplying by a fraction, we're dividing by its reciprocal. All right, we're making this a little bit more complicated looking, but that's okay, because ds dt, in the previous video, when we talked about the arc length parameter, I said that later on we would need to know that s prime of t was equal to the magnitude of r prime of t. And I said that, we're going to need this later, and I'm going to remind you of it, and you should think back to it. And this is when we're going to need it. ds dt is equal to the magnitude of r prime of t. We used the first part of the fundamental theorem of calculus to do this. And so what you notice is that what we've just done is we computed the derivative of r with respect to the arc length parameter, the r prime of s. We've just computed and shown all that it was equal to r prime of t divided by the magnitude of r prime of t, which is what we just defined as the unit tangent vector. Okay? And so one of the nice things about the arc length parameter is that when you compute derivatives using the arc length parameter, those vectors are automatically unit vectors. And in a lot of applications, unit vectors are sort of a really nice thing to use because there's only one unit vector in a given direction. Right? We could all, if we have a direction that we care about, we could all write down a different vector that describes that same direction. And in order to see if we're using the same vector, we'd actually have to compute them to see if one's a scalar multiple of the other. But if we all have unit vectors, then it's really easy to tell if they're the same direction or not because they're either going to be equal or they're not. And so getting unit vectors is a really useful thing to do. And if we're able to have a function whose derivatives are always unit vectors, it saves us the work from having to scale them all down to length 1 at the end of every problem. Right, so let's look at an example where we find a unit tangent vector for a particular curve. So let's say we wanted to find the unit tangent vector for the curve defined by the vector function r of t with components cosine t, sine t and cosine of 3t on the interval 0 to 2 pi. So we just need to compute the vector capital T of t that we just defined a little bit ago. So to do that, we have to start by looking at r prime of t. So r prime of t is going to be the derivative of cosine, which is negative sine, the derivative of sine, which is cosine, and the derivative of cosine of 3t, which will be, by the chain rule, negative 3 sine of 3t. So that's our derivative r of t, or r prime of t. We then need to compute its magnitude. So this will be square root of negative sine t squared plus cosine of t squared plus negative 3 sine of 3t, quantity squared. All right, so this will be sine squared plus cosine squared of t plus 9 sine squared of 3t. Right, and so of course the first two terms add to 1, and so we get the square root of 1 plus 9 sine squared of 3t. Right, so that is our magnitude. And so our unit tangent vector is r prime of t divided by this magnitude that we just computed. So we can write it in a couple different ways. Usually the easiest way is to write it with the scale factor out front. So it's going to be 1 over the square root of 1 plus 9 sine squared of 3t multiplied by this vector, negative sine t, cosine t, negative 3 sine of 3t. Right, so this would be the unit tangent vector to this curve. Now notice, because I used the parameter t here instead of picking a constant t naught, this gives me the unit tangent vector at every point on this curve. So if I want, if I take the point at t equaled pi, for example, all I would need to do is compute capital T prime of pi by evaluating this vector at pi, and that would give us the unit tangent vector at the point on the curve r of pi. And we could do the same thing for when t is pi over 2, or 3 pi over 2, or 5 pi over 4, any of these values. So we've computed a tangent vector at each point on our curve. So we've now developed the unit tangent vector, but the section, this video here is called the unit tangent, normal, and binormal vectors. So we want to come up with some other vectors as well that are meaningful to the curve itself. And so to do that, we're going to start with the following theorem. So if we're given a smooth curve given by the vector function r of t, it turns out that the unit tangent vector that we just computed and another vector, which is going to be t prime of t, so the derivative of the unit tangent vector, it turns out that these vectors are always going to be orthogonal to each other. Right, so t, the unit tangent vector, and its derivative, t prime, will be orthogonal vectors. Right? And so in order to, we're actually going to show this. It's not very difficult to see. It's just using properties of dot products. Right? As soon as I wrote down the words orthogonal, you should have thought of the dot product. All right, so our goal here is going to be to show that t dot t prime is equal to 0. So to do this, to show this, we're going to start off with a couple things that we know. So for example, one thing that we do know is that the magnitude of the unit tangent vector is equal to 1 for all values of little t. Right? This is the unit part of the unit tangent vector. Right? So this we know is always going to be 1. And in particular, that tells us that if I take the dot product of t with itself, right, we know it in general, we know this is always the magnitude of that vector squared. And that would mean this is equal to 1 squared, or 1. So t dot t is equal to 1. Right? Now, we actually saw an example like this. It was pretty similar. In fact, when we talked about the dot product in previous videos. So what we're going to actually do here is we're going to compute the derivative of t dot t, the derivative of t dot t in two different ways. Right? So we're going to compute the derivative of t dot t, and we're going to do this, like I said, two different ways. So the first way is we're going to use the product rule. So there was a product rule for the dot product when we took derivatives. And so that product rule was that we're going to take the derivative of the first vector, dotted with the original second vector. And we're going to add to that the first vector, dotted with the derivative of the second vector. Right? And when we do that, we see that these two terms are really the same. T prime dot t and t dot t prime are the same. The dot product is commutative. So this ends up being 2 times t dot t prime. Right, so this is the product rule for the derivative. But on the other hand, we just showed that this function t dot t is equal to 1. So this is also equal to the derivative of the constant function 1, right, which we know is equal to 0. Right? So I apologize for kind of working around the screen in a weird way. It's what I have to do with the limited space I have on my iPad screen. But what we can see here is that 2 times t dot t prime is equal to 0. And so if we divide both sides by 2, we get the goal that we wanted. And that is that t of t dot t prime of t is equal to 0. And that verifies our theorem that t and t prime are then orthogonal because their dot product is equal to 0. So now that we know that the derivative of t is orthogonal to t, we're able to define the other vectors that we would like to talk about. So for this definition, we're going to assume that r of t and the tangent vector, unit tangent vector t of t, are smooth. Right? So this means that their derivatives exist, are continuous, and are not equal to 0. Right? So once we know this, we can define the unit normal vector. So the unit normal vector is going to be defined as capital N of t. And it's going to be the derivative of t divided by the magnitude of that vector. Right, so this is going to be normal. It's going to be orthogonal to the unit tangent vector, so it'll be orthogonal to the curve. And the the fact that we're dividing the vector by its magnitude, we're scaling it by 1 over the magnitude, tells me that it will be a unit vector as well. Right? And so the unit normal vector is defined in this way, and the unit binormal vector is defined as capital B of t, and it's going to be the cross product of the unit tangent vector and the unit normal vector. Right, so again, this will be a unit vector. You can see that when you compute out this cross product. But if you do have a product if you have 2 unit vectors like this and we take the cross product, then we will get a magnitude of 1. And so it will be a unit vector. And so what this is basically a third vector, which is orthogonal to both the unit tangent and the unit normal vector. Right? And that's exactly what the cross product produces. And so the punchline here is that at each point of the curve given by r of t, we have these 3 vectors, right? T of t, n of t, and b of t, which create an orthogonal system of vectors conveniently called the T and B frame. Now we're not going to get too much into this other than just looking at how to compute it. But for those of you that might be using this in a physics or engineering setting, the T and B frame is often something that's used to help simplify calculations that might be at weird angles. Usually, in physics, you sometimes will set your coordinate system, maybe not in the horizontal and vertical directions, but rather in the directions of the motion, so that you can understand the motion a little bit easier without having really complicated formulas. And so the T and B frame is sort of the same thing, but in 3 dimensions. We're going to sort of, at each point of the curve, you can reset a 3-dimensional coordinate system with these 3 vectors as sort of your unit basis vector, standard basis vectors, and then you can write everything in terms of the T, N, and B vectors. And after we compute the next example, I'll show an image of what I'm talking about with these T and B frames. All right, so let's say we wanted to find the unit tangent, normal, and binormal vectors of the helix given by r of t equals cosine t, sine t, and t. Right? So this is our very standard helix that we looked at as our first example of a vector function. It goes up, starts in the xy plane when t is 0, and it goes up circling the z-axis. And so, this is not a very difficult thing. We're just taking derivatives, finding magnitudes, forming a unit vector, and then repeating the process. And then to find b, we take a cross product. Okay? So to start, we want to find the unit tangent vector. Right? So we've already done an example of this, so we'll go through this one kind of quickly. So r prime of t, we're just going to take the derivative of this vector, negative sine t, cosine t, and derivative of t is 1. And then we take the magnitude of this vector. Right? So this is negative sine t squared plus cosine t squared plus 1 squared. And so this is just the square root of 2, right? Sine squared plus cosine squared is 1, and 1 plus 1 is 2. And so our unit tangent vector, t of t, is 1 over square root 2 times our derivative vector, negative sine t, cosine t, and 1. Okay. And so there is our unit tangent vector. Right. Right, so to find the unit normal vector, we're going to take the unit tangent vector that we just found and compute its derivative. Right, so we will have 1 over square root of 2 out front. Remember, that's a constant. We don't want to forget that. But it just kind of comes along for the ride. And then we differentiate each of the terms. So the derivative of negative sine is negative cosine. The derivative of cosine is negative sine. And the derivative of 1 is 0. And so our third component is 0. We then want to compute the magnitude of this vector. And when we scale a vector by a constant like 1 over square root of 2, we can think of that as just multiplying the magnitude by 1 over square root of 2 as well. So I'm not going to distribute that out, although you could, but just to make the square root computation here a little bit easier, we're going to not do that. So this will be just negative cosine t squared plus negative sine t squared plus 0 squared. And of course, this whole square root part here is just going to be the square root of 1. And so this is just equal to 1 over square root of 2. All right, 1 over square root of 2 times 1. And so the unit normal vector, capital N of t, is going to be the unit tangent vector, 1 over square root 2 times the vector negative cosine t, negative sine t, 0, divided by its magnitude, which is 1 over square root of 2. And of course, these cancel nicely. And so we're just left with the vector negative cosine t, negative sine t, and 0. So this is our this is our unit normal vector. So our last step is to find the unit binormal vector. All right, so this is the cross product of the two vectors that we've previously found, so t cross n. So if we use the determinant form, so we have our vector t, which is negative sine of t over square root 2, cosine t over square root 2, and 1 over square root 2. And our normal vector, our unit normal vector, is negative cosine t, negative sine t, and 0. Now, before I compute this, one thing I want to point out is that, like, when I wrote down the unit tangent vector here, we do need to include that constant 1 over square root 2 that we had out front. And you know, you can leave the vector, and if you're just talking about the vector, you can leave it as constant times the vector, but we do need that vector, that constant scaled here, and that way what we get here is guaranteed to be a unit vector. Okay. Right, and so when we go ahead and do this, when we do the I term, we're going to get a 0 minus a negative 1 over square root of 2 times sine, so this will be sine of t over square root of 2 times I, a positive one. And then it's minus. Remember, with the cross product, the second term is always a negative. And so the j term, we're going to get 0 minus cosine t over square root of 2. And so this will be cosine of t over square root of 2 times j. And the third term is we do get a little bit more complicated one, at least initially. So we're going to end up with sine squared of t over square root of 2 minus a negative, which becomes positive, cosine squared t over square root of 2. That's all times k. And so, of course, not hard to see here that sine squared of t over square root of 2 plus cosine squared of t over square root of 2, that ends up just becoming 1 over square root of 2. And so our vector, if we write it in component form, is going to be sine t over square root 2, cosine t over square root 2, negative cosine t over square root 2, and 1 over square root 2. And if you wanted to write it with that 1 over square root 2 out front, you certainly could. And then the remaining components are sine of t, negative cosine of t, and 1. Right? So this would be our binormal vector. All right, so I promised a little bit of a more explanation of the TNB frame after we did this example. So again, I apologize for the blurriness. But in this case, what we have here is the black curve representing the helix that we just studied, given by cosine t, sine t, and t as the component functions. And at each point, they've drawn 5 points here on the curve. And at each point, they've drawn 3 different vectors. And so at each one, the red vector represents the unit tangent vector, the n vector represents the unit normal vector, and the b vector represents the unit binormal vector. And so at each of these points, because these 3 vectors are all orthogonal to each other, we know they're going to make a little coordinate system that looks much like the xyz coordinate system. But of course, at each point, it's a little bit different. So the tangent direction is in the direction the curve is traveling at that point. The normal vector is orthogonal to the curve at that point. And the binormal vector is then defined to be orthogonal to both of those directions. Right? And so if you were interested in studying something in real detail about this particular point on the curve, this point right here, if you use the normal xyz coordinates to describe what's going on there, everything is going to be done at an angle. The curve is moving at a weird angle compared to the x, y, and z plane. And so all of your calculations that you're going to want to compute, whatever is going to work, whatever you're going to be doing, is going to be just very difficult to do, very tedious. But if you could reframe yourself so that t, n, and b were your coordinate system, then things work out really nicely because you're looking at the 3 most important directions of the motion. The direction in the direction of the motion, the direction normal to it, and then the third direction, which is the right-hand ruled third direction based on those first 2. And so typically the TNB frame is used in applications when you want to focus on a particular point in which the normal x, y, and z coordinates just will be very ugly and tedious to use. One thing we're not going to do in this course, but you might see if you do any kind of physics or engineering in the future, you can also then, once you have these 3 vectors, you can go on and define 3 coordinate planes in terms of these vectors, and then sort of develop everything that we've done with vector functions in terms of these 3 vectors and those 3 coordinate planes.